Hello and welcome to another video on error messages in Mplus. My name is Geiser. On this channel I present weekly statistics tutorials, often related to structural equation modeling, latent class analysis and multi-level modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button in case you like this video. In this video I want to discuss a common error or warning message in Mplus that can occur when you run structural equation models and that many people are confused about. And that is a warning about a non-positive definite latent covariance matrix. And I want to give you an example here of such a warning message in a confirmatory factor model and show you what this means and also give you some ideas about what the causes of this issue are or might be and how it could be fixed. So here in this example, I have a second order confirmatory factor analysis model that is pretty simple. I have three first order factors. As you can see here from my model statement, I have in this example a cognitive ability test that I'm analyzing, or the scores from this test, with a verbal component, a quantitative or numerical component, and a figural component. So it's basically a reasoning test with different material, verbal material, numerical material, and figural material. And so I'm using here a model with three first order factors, a verbal factor, a quantitative factor, and a figural factor. And each factor has two indicators. Those are test or subtests that correspond to these different reasoning tasks. And then as a second order factor here, I have a general factor, or a factor that I called the gen factor, which has the three first order factors as indicators. The idea here being that there's a general reasoning factor, so to say, behind these first order factors, because all tests have in common that they measure reasoning ability, although they use different materials. So we have, so say, specific variance related to the material, a specific verbal factor, a specific quantitative factor, and a specific figural factor. And so sometimes when we have such a faceted design, people use second order models, or they might try to use bifactor models to parse out general and specific variance. And so let's take a look at what happens here in Mplus when I hit the run button for the second order factor model. You can see there's a warning message related to missing data, but this is not the one that really interests us here. This merely says that there are cases here in this data set that have missing values on all 6 indicator variables that are used in the measurement model, and therefore they cannot be used. And this is simply due to the fact that this is a sub-data set that I drew from a larger data set, and so these 131 cases had scores on other variables that were not included in this sub-data set that I am using here, and so this message therefore can be ignored. All other cases are included here in this analysis, whether they have complete data on these 6 variables or partially missing data, because Mplus uses full information maximum likelihood estimation with missing data. If this interests you more, then you can check out the videos or the playlist that I have on this channel on missing data analysis in Mplus, where I discuss this in more detail. So now let's focus on the actual warning message that I want to discuss here. So let's scroll down a little bit, and after the descriptive statistics, you can see that a standard message appears that says the model estimation terminated normally. So this means the model did converge. There was convergence to a maximum likelihood solution, and Mplus was able to arrive at fit statistics and a set of parameter estimates for this model. However, something didn't go quite right. You can see that there's this warning here that says the latent variable covariance matrix psi is not positive definite. This could indicate a negative variance, residual variance, for a latent variable, or correlation greater or equal to 1 between two latent variables, or a linear dependency among more than two latent variables. Check the TEC4 output for more information. The problem involves variable FIGU. So FIGU is one of the first order factors. There's something about a variance or residual variance or correlation estimate related to FIGU that is not quite right, or there's some sort of linear dependency involving this variable. So let's check this out, what this means, because oftentimes people are then scared or confused and they don't know what to do. They don't know whether they can use the model, what this actually means. So let's go down a little bit. And when you look at the fit statistics here, you can see that actually this model looks really good. So the chi-square test of model fit is non-significant. P-value is 0.35, so that's larger than the common alpha level of 0.05, which means the model would not have to be rejected at the 0.05 level. That looks pretty good. The RMSEA is also quite low. CFI and TLI are quite high, close to 1. And also the standardized root mean square residual, or SRMR, that is a summary measure of the standardized residuals, also looks really good with a value close to 0. So the model fits these data well. So what went wrong? Let's take a look at the parameter estimates. When you scroll down, the loadings look normal. You can see one loading is always fixed to 1 per factor for identification. By default, that's the first loading in Mplus. So that all looks normal. We get some intercepts that look normal. A variance of our general factor is estimated. And then we have residual variances. And you can see we have residual variances for the observed variables. So those are the error variances for the indicators. And then we also have residual variances here for the latent first order factors, because those are regressed on, so to say, the general factor. So they are a function of the general factor. And so the general factor does not explain all the variance typically in the first order factors, or at least that is the idea behind the second order factor model, that there is some specific variance. So the general factor explains some of the covariance of the first order factors because they all measure reasoning, but then they all have also specific variance because they use different materials, verbal, numerical, and figural material. And so here you can see that something went wrong, because we do have a negative residual variance estimate for the first order factor FIGU. So this means that the general factor explains more than all of the variance, so to say, in this figural factor, which is not possible. So at most, the general factor could explain 100% of the variance in this figural factor, but not more. So a negative variance or negative residual variance estimate doesn't make any sense, because that would mean a factor has an R² value greater than 1, more than 100% explained variance by the independent variable, which here is the general factor, and that doesn't make sense. So we call this an improper solution, or we call this a solution with an out of bounds or out of range parameter estimate. Variances are bound to be positive. They could be 0, but they couldn't really be negative logically. So this estimate doesn't make sense here, and this is the issue. Now let's take a look also at the standardized solution, where you can see this also from different estimates. So you can see the first order factor loadings are all proper and okay. They're in the normal range, so they don't exceed 1 for a standardized loading in this model where each variable loads only onto one factor. The standardized loadings couldn't be larger than 1. And so that's the same also for the general factor. You can see the general factor loadings here, and they also couldn't be larger than 1 normally, logically, but you can see there is a loading that is slightly above 1.0, and that's the loading for the figural factor. And this is exactly the same issue that shows that here the general factor would be correlated with the figural factor more than 1. So that this standardized loading indicates the correlation between the first order factors and the second order factor, and so a correlation above 1 doesn't make sense. So this is the same issue that also reflects this negative residual variance. And there's another place or two other places where you can see this also. So that's the standardized residual variances again show a negative value here. And also when you look at the latent variable r squared at the very bottom of this output, you can see that the r squared for figu is undefined. So this means it doesn't make sense to have an r squared greater than 1, and so Mplus will not print it because it's not defined. It's funny that Mplus does print negative variances and standardized loadings above 1 when they could not be above 1, but for r squared it doesn't do that, and they'll tell you right away that this is not defined and it doesn't make sense because you can't have more than 100% explained variance. So you see that you don't even have to request the TEC4 output where you would have the latent covariance matrix and the latent correlation matrix. You can take a look at the parameter estimates, and oftentimes you will find estimates then that explain this warning message about a non-positive definite latent covariance matrix. Now, this is not always the case. So sometimes you have a model that is all proper, that has parameter estimates that are all within the proper bounds. There are no correlations that are improper, no variances that are improper. And so then the reason could be that there are linear dependencies among latent variables. And that can happen when you have factors, latent variables that are very highly correlated, such that one factor is a perfect linear function of a set of other factors in your model. And so then you may not see a problematic estimate, but there could be, so say, behind the scenes linear dependencies in your model. And so then you could take a look at the TEC4 output and see more closely how highly all those factors are correlated and how this could lead to a non-positive definite latent variable covariance matrix. Now, I do want to talk about a little bit about how this can happen, what are reasons for this, and how you can fix this problem. Now, the interesting thing about this model here is that a model version without the second order factor, so when you delete the second order factor from this model and you just simply allow the 3 first order factors to be correlated freely, you get a solution that is proper. So in this case, when you run this again, you delete the second order factor model, you just simply have 3 correlated first order factors, then you get a model that has the same fit. It's an equivalent model and it's proper. So really here the problem comes in once you start to model those 3 covariances in terms of a second order factor. And that's interesting because those models are completely equivalent and they have the same fit, because with only 3 first order factors, the second order factor is just identified because it has only 3 indicators. And so now therefore the reason for this is the inhomogeneity of the first order correlation pattern. And we can take a look at that by running this model again without the second order factor model. So let's close this here. So I can just simply comment out the general factor by putting an exclamation point here. That an Mplus then becomes a line of comment. So you get rid of this without having to delete it and retype it. It becomes ignored by the program. And let's also check out the TEC4 output for this model with just correlated first order factors. So when I do this, when I have just a set of first order factors in Mplus, they are by default allowed to correlate. Yeah? So I'm getting now a model where I have only first order factors and they're just simply freely correlated. So let's take a look at this also. Now we can see that there's no warning message about non-positive definite covariance matrix here. The model estimation terminated normally, and you can see that the fit of the model is identical. We get the exact same chi-square test as before, same degrees of freedom, same p-value, same RMSEA, same CFI-TLI, and same SRMR, because those are equivalent models. Again, it's because we have only 3 covariances among first-order factors, and in the second-order factor model, we estimate 3 parameters, the 2 loadings that are not fixed, the 2 second-order factor loadings that are not fixed, and the variance of the second-order factor. So those are models that are equivalent, and the second-order factor is just identified, so to say. And so you can see here we now have the 3 covariances of the first-order factors as parameter estimates, in contrast to, or in replacement for, the second-order factor loadings and the second-order factor variance, but the model or the fit to the covariance structure, the latent covariance structure, is the same. And so this is all proper. Now when we take a look at the correlations of the first order factors, which you find here in the standardized solution STDYX, those are the latent correlations here, then you can see that they are all substantial. So it kind of seems to make sense that these factors all measure reasoning ability, that they share a common factor, so to say. So you can see the highest correlation is 0.88, and there's one that's 0.855, and there's one that's 0.75. So that kind of does seem to make sense to say, oh, these have a common underlying reasoning factor or something like that. Another place where you can see this is from Tech 4. When you go down here, Technical 4 output, and you scroll down a little bit, you get the estimated covariance matrix for the latent variables, and you also get the estimated correlation matrix further down below, estimated correlation matrix for the latent variables, and here you get the same values printed again with their p-values, standard errors, and so on. And so now, what is the reason that we're getting an improper solution when we fit this G factor or general factor to these correlations? The reason is that they're not homogeneous. You can see 2 of these factors are more highly correlated. The figural factor is more highly correlated with both the verbal factor and the quantitative factor than the verbal factor is with a quantitative factor. And so this inhomogeneity, there's a substantial difference in these correlations. And so the second order factor structure kind of expects that these correlations are all about the same, and so therefore you get this negative variance estimate, and it basically means that one of the factors is identical, the figural factor is identical to the general factor because it has no residual variance or no specific variance, so those are perfectly correlated. We saw that the standardized loading was 1.003 between the figural factor and the general factor. So in other words, the figural factor really becomes the general factor, and so that's not quite what we want. And so this is a problem that we actually often see with second order factor models and also bifactor models, that one of the specific factors has no specific variance and becomes identical to the G factor. And I'm going to discuss this issue more in a separate video, but note that this is a frequent source of a frequent explanation for improper solutions, is that simply the second order factor structure doesn't really fit or doesn't really make sense for a latent variable covariance or correlation matrix. Now, other reasons why this can happen is simply due to chance, due to sampling error, so say bad luck that we, in our sample, due to sampling error, we have a constellation of values of covariances that are generating this improper solution, even though the population model is correctly specified and has the right structure, but in our sample just simply we have sampling error that leads to an improper solution. So that can happen. Other kinds of model misspecification, over-factorization, when you have too many parameters, too many factors. This could be a problem when your sample maybe is too small. Then those issues can occur more frequently due to sampling error and just simply a sample that is too small. So those are some things, and what you could do is make sure that your model is correctly specified, that your sample isn't too small, and think about the structure of the model, whether it really makes sense for your data. I hope you found this video useful to learn more about non-positive definite matrices and warning messages in Mplus. If you liked the video, then please don't forget to hit the like button. Also, don't forget to subscribe to this channel and check out the description for additional free resources and workshops, and I'll see you next time.